In section 3 of chapter 12, we're going to be going over, again, another conic shape. This is actually one of my favorites. We're going to be going over the oval-looking shape, which is actually mathematically referred to as the ellipse. Again, as a review, if you have two coins stacked on top of each other with the points pointing at one another, and you take a slightly diagonal slice, that's what's going to generate the ellipse, the oval-looking shape. Now, if you think about it long enough, there's actually two different types of ovals that you could create. The two types are, the first type, it's stretched in a horizontal direction, that is left and right, more than it's stretched in a vertical direction. The second subtype is, well, what happens if it's stretched to be taller? What if it's stretched in the vertical direction more and the horizontal direction less? So the first thing, before I go into actually describing the equation, how to graph them and all that, is I want to start defining the vocabulary, because the vocabulary for each of these different types of ellipses is similar, but there are some key differences. The names kind of switch depending upon what type of ellipse you're talking about. So first, if we're talking about the first ellipse that is stretched more left and right than up and down, if you take these little endpoints here and here, those are called the vertices. Vertices. It's kind of like the word vertex, but there's more than one, so it's vertices, plural. Next, there's going to be something that is called a major axis. The major axis represents the axis that goes through the center of the ellipse, but is going in the direction that the ellipse is stretched in more. So this ellipse for this one is stretched more in the horizontal direction, so its major axis is shifted left and right. And then there's also a minor axis. Now, if you wanted to, these locations do have a name. They're called minor vertices, but we typically don't really use them all that often. So they don't typically get mentioned. This location right here, that's the center. The last thing, because we are dealing with conic sections, and conic sections are kind of defined by focal points, is there are going to be focal points. In fact, there's going to be more than one. A parabola just had one. This is actually going to have two focal points. Those, when there's more than one, it's not called a focus, it's called a foci, because there are two of them. These are the major labels for an ellipse that is stretched horizontally more than it is stretched vertically. If you're dealing with a type 2 ellipse that is stretched vertically more than horizontally, some of these things change a little bit. The vertices are no longer left and right from each other. The vertices are now up and down. Now, the colors are going to seem a little bit weird, but this is more in line with the algebra than it is with the two shapes in conjunction with each other. So just focus on the words I'm writing. The colors will make sense when I go to the second set. But the axis that is in the direction it is stretched in, that is to say, the axis up and down in this case, this is referred to again as the major axis. The axis in the minor direction, that is left and right, is called the minor axis. Where those two axes meet is the center. And now the focal points are no longer going to be left and right, they are going to be up and down. Those are the focal points, the foci. All right, now that we've got the vocabulary out of the way, we have an understanding of what I will reference as what, we're now ready to start talking about what is called the graphing form of an ellipse. Now, I know that there are two forms to ellipses, but believe it or not, for the graphing form on how we write the equation, there's actually only one equation. There's not a different one for each equation, or for each shape. So here is the formula on how to write an ellipse. It is the quantity of x minus h quantity squared plus the quantity of y minus k quantity squared. Now at this point I want to pause because this looks really, really familiar. This looks, actually right now, it is the equation of a circle. Because ellipses actually come from circles. The only difference between an ellipse and a circle is uniform in all directions. It has a constant radius. So normally we go like equals the radius squared. But ellipses are stretched differently depending if you're talking about the horizontal stretch and compression versus the vertical stretch and compression. The thing that separates an ellipse from a circle is that it is a circle, but it's stretched or compressed in one specific direction more than the other. So that means we actually need a stretch and compression factor for both the x value and the y value, and they're going to be different from one another. So we can't have it equal to a radius, it's going to be equal to 1. And the way we write the stretch and compression factor is we divide. So technically what I'm about to write is not the technical stretch and compression factor. You can kind of think about it as the reciprocal stretch and compression factor, but it'll do just fine. It is going to be over a squared, and then it'll be over b squared. So that's why I chose the colors I did in the examples, the diagrams above, is because the a value will dictate how far we're moving in a left and right direction, because it's underneath the x value, which dictates left and right movement. And then the b value in purple will determine how we stretch and compress in the vertical direction. All right, so let's do an example. Super quick, super easy. In fact, I like these. They're kind of similar to circles, in fact. Let's say we have x minus 1, quantity squared over 49. And that'll be plus the quantity of y plus 5, quantity squared over 36 is equal to 1. All right, well, I know that I'm going to be shifted right 1 because of the 1 that is being subtracted next to the x. And I have a y plus 5, which tells me I'm going to be going down 5. So there's the center of the circle. And then the value underneath the x is a 49. That is the a squared value. I don't want the a squared value, I want the a value. So we're going to square root this. The square root of 49 is 7. So in the x direction, left and right from my center, I'm going to go right 7 and left 7, and those will find the vertices in the x direction. So let's go right 1, 2, 3, 4, 5, 6, 7. Left 1, 2, 3, 4, 5, 6, 7. All right, there's 2 of the vertices. Next, the value underneath the y term is a 36. That's my b square value. But I want my b value. So if I square root the 36, I will get 6. That is how we're going to move from our center up and down. So I'm going to go up 6. And I'm going to go down 6, which kind of takes me off the graph, but that's fine. And there's my ellipse. Now you might look at this and maybe think, well, Silva kind of sucks at drawing. But this kind of looks more like a circle than like an oval shape. But that's because if you look at the stretch and compression factor for the vertical and horizontal, this one's going to be a 7, this one's going to be 6. Those are relatively close numbers. 6 and 7 are right adjacent to one another. So if you graph this, it'll look a little bit more oval shaped than what I did freehand, but it is going to look a little more rounded. If this was instead like a 1, meaning I would just go 1 left, 1 right, then you get a really, really obvious elliptical shape. Now I haven't done the focal points yet. I haven't done the foci. We're going to do that in a little bit, but I want to mainly focus on how do we graph the center and the 4 vertices, both the major and the minor. Now one question or a few questions that I do get that I want to address before we move on is I have had students say, okay, well what happens if this is not equal to 1? Let's say this is equal to 2. This is equal to 2, then it is not in the graphing form. The graphing form has to have it equal to 1. So if this is equal to 2, I would multiply everything by 1/2 in order to turn it into a 1. What if this is not an easily square rootable number? Well, then that just means when we find our vertices, it's going to be decimal values. Like let's say this number was a 2, then I'm going to go, like what is the square root of 2? It's like 1.6 something, 1.7 something. That's the amount that I'm going to go. So most of the time, I'm going to give you nice and easy numbers to square root, but that's not necessarily always going to be the case. Once again, I kind of like talking like, what the heck is the point? Because ellipses have a lot of practical applications. But first, I want to talk about the formal definition of an ellipse. The formal definition of an ellipse is a closed plane curve generated by a point moving in such a way that the sum of its distances from two fixed points is constant. The heck does that mean? That means if you have 2 points, any points in space. Now we're having them horizontal from each other, but I could have them diagonal, I could have them vertical, I could pick any 2 points in space. And then I am going to generate another dot, where I take the distance from that dot to the first focal point and the distance from that dot to the second focal point. And I add those distances together. Let's just say the distance when I add them together was 10. I'm going to generate a bunch of coordinates whose distances are also 10. So if I pause it like there. Then that would mean, like, let's, again, example was like right here, and I said this distance plus this distance was 10. Then if I pick this coordinate, this distance plus this distance is 10. If I do that for all of the coordinates, they will all be the same. So this is how you generate an ellipse. The sum of the two distances is equal to each other. That is what generates the shape of an ellipse. All right, awesome, superb. Why is that useful? Well, these focal points actually have a really, really interesting feature to them. If you have 2 focal points here and here, and just like the parabola, where I had one of the focal points, I shot out rays in all directions, whether it be light rays, sound rays, whatever. I shoot them out in all directions. What happens when they hit the wall of the ellipse is something super, super easy. If you shoot an infinite number of rays starting at one of the focal points, they reflect off of the outside of the ellipse and they reconvene at the other focal point. That allows you to do some really, really interesting things because let's say you're in an elliptical shaped room, like an office, like in an oval office, and you are standing at one of the focal points. And someone else is standing at the other focal point. And let's just imagine this room is really, really, really large. Like this room is ridiculously large. It's the size of your house large. And you're having a party. Like there's people all throughout the room. Loud, loud party. If you're standing at one focal point and someone else is standing at the other focal point, even with all the noise and commotion that's happening around you, if this person whispers, this other person will hear it, even across the entire room, even with all this other noise happening. Because when this person talks, all of the sound that they produce gets shot out from that central focal point, bounces off of the walls, and then all the sound waves reconvene back at this other focal point. That allows you, if you're at 2 focal points in an oval shape, an elliptical shaped room, and you are in the focal point with another person at the other focal point, you can have a full-on conversation no matter how much noise is happening around you. Now, if you want to see some videos, I didn't have enough time to actually embed these in here, plus there's also copyright stuffs, but I did create 2 QR codes. These will actually go through 2 examples that actually showcase how this is used in the real world and where you can see this in certain state buildings. They're mainly in the East Coast, but there have been other times when you can use this as well. All right, now that we got this, let's start doing some problems. Now, I'm talking about the focal points, the 2 focal points. I've been talking about them a lot. How the heck do we find them? Well, remember, when I talked about the definition of a focus, or the foci, for an ellipse, and where the definition of an ellipse comes from, it was taking the sum of 2 sides of basically a triangle. It was taking the sum of the distances between a point and the 2 foci, and saying that they are constant. we have equations that deal with triangles like that. It's the Pythagorean theorem. And that's actually where the focal point or the focal length comes from. C, the focal length, squared is equal to, and now technically we don't know which one is positive or negative and all this stuff. We have kind of an issue of making sure that this value should remain positive, but that's okay. We have an equation or a way of making sure numbers are always positive. It's the absolute value of a squared minus, get the right color, b squared, absolute value. Now technically you don't need to use these absolute values as long as you take the bigger one, whatever one the bigger one is, and then subtract the smaller one. All right, so let me do problem number 1 as an example. Problem number 1, the C value, the focal length, is equal to the absolute value of 25 minus 9 absolute value. Now, I don't need the absolute values in this case because the first number is bigger. Now, if I swapped these two and said 9 minus 25, then I would need the absolute values. But ultimately, C is going to be equal to the absolute value of 16, which means C is equal to 16. This is going to be my focal length. Oh, sorry, I forgot the square part. Which means when we square root both sides, don't forget your plus or minus, we are going to get C is equal to plus or minus 4, which kind of makes sense because we get 2 focal points, we need 2 focal lengths. So if I was to graph this, I know I'm going to be shifted left 3 and up 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. That's right here. This is my center. And I know that the square root of 25 is 5, so in the x direction I'm going to go 1, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5 to the right. I know the square root of this number is 3, so I'm going to go up, 1, 2, 3. I'm going to go down, 1, 2, 3. There is my ellipse. And I know the focal length is plus or minus 4, so from my center, I'm going to go right, 1, 2, 3, 4, and I'm going to go left, 1, 2, 3, 4. And those will be my 2 focal points. And now I have finished graphing the ellipse. Well, what happens if they're not all done up like the way that we like? Like problem number 2, I don't have it equal to 1, and I'm not dividing, I'm multiplying. Well, problem number 2, really straightforward. I want it equal to 1. First step, always make sure that the equation is equal to 1. So first step is I'm going to divide everything by 32. Because that will give me, well, 8 divided by 32. That's a simplifiable fraction. That is just going to be, not 8x squared, x squared over 4 plus y squared over 16 is equal to 1. So we're not shifting left or right. We're not shifting up and down. That means the center is right here. In the x direction, the number underneath the x squared is 4. The square root of 4 is 2, so I'm going to go right 2 from my center. I'm going to go left 2 from my center. The number underneath the y squared is 16. The square root of 16 is 4, so from my center I'm going to go up 4, and I'm going to go down 4. Here's the shape of the ellipse. The last step we need to do is find our focal point. The equation is c squared is equal to the absolute value of the larger of the two, 16, minus the smaller of the two, which is 4. As long as you take the larger of these two numbers, the 16, and subtract the smaller of those two numbers, the 4, you technically don't need the absolute values. But if you don't know which is which, then you definitely do need it. That means c squared is going to be equal to 12. Oh, crap. I can't square root 12 very nicely, because if I square root both sides, don't forget the plus or minus, you'll get c is equal to plus or minus 2 root 3. I don't know what that is, so I got to type that into a calculator to figure out what the decimal approximation is, which is 3.46. This is my focal length. That means, sorry, plus or minus, that means I'm going to have to go up 3.46 and down 3.46. Is it perfect? No. But is it accurate? Yes. So do realize that for most ellipses, If you want to make all 4 of the vertices nice, that typically, but not always, but that typically means the foci are not going to be pretty numbers. If you want the foci to be pretty numbers, then that typically means the vertices are not pretty numbers. So you have to give and take. One of these is not going to be easy, and the other one is going to be difficult. The last iteration I want to do is what happens if I just straight up tell you what the vertices and the focal point, and one of the focal points, are. All right, I like visualization, so I'm actually going to graph these first. The vertices, which are the major vertices, are 5, -3, 1, right 5, down 1, 2, 3. So here's a vertice, the major vertice. The other one's at -1, -3, which is right here. And then one of the focuses is at 3, 1, 2, 3, -1, 2, 3. Here's one of the focuses. Well, I automatically know that the center is going to be right here. And that means the other focus is going to be right here. The only way it can work, because they're mirrored of each other. So I need to find the minor vertices. So I know that this is shifted 1, 2, 3 to find the major vertice. So this cannot be higher than here. It has to be somewhere in this range. So it could be like 2.9, or it could be like 2, or could be 1. But I know it can't extend beyond 3, because otherwise the foci would be in the vertical direction. So I know that we're trying to find the minor axis. All right, so let's list what we got thus far. So thus far in the equation, I know that I've gone, for my center, I've gone right 2 and I've gone down 3. So I know it's going to be the quantity x minus 2 quantity squared plus the quantity of y plus 3 quantity squared. I know it's going to be equal to 1. I also know that in the x direction, the major vertice is 3 jumps away, which means the number underneath is going to be that a value squared, which is 9. What we do not know is we do not know the b value. That's what we need to figure out. But here's what we do know. We know that the formula, c squared is equal to the absolute value of a squared minus b squared. We know that, and we know 2 of those values. I know what the c value is, because I know that I jumped 1 unit. So I know c is 1. I know that 9 is the bigger of these 2 values, so I know it's going to be 9, or if I wanted to, I could write 3 squared, minus the b value squared. I know that this is going to be my formula. So 1 is equal to 9 minus b squared. Subtract the 9 to the other side, I get -8 is equal to -b squared. Multiply both sides by a negative, I get 8 is equal to b squared. Square root both sides, don't forget the plus or minus, and I will find that b is equal to plus or minus 2 root 2, which is equal to plus or minus 2.83, roughly. There is where my other vertices are going to be. It's going to be up 2.83, somewhere like around there, and then down 2.83, which is somewhere like around down there. Here is my ellipse. And now I'm ready to write my equation. I need to square this in order to figure out what goes here. But that's the same thing as squaring this. But I already know what this squared is because I already had it here. B squared is equal to 8. So it's just an 8. There's my equation. And that's my graph to the right. And we are now done.